Hey, grade 11s, primarily cohort B and O. Just want to give you a little update of what went down today in the classroom. As I've said to most of you, we're going to have to treat this primarily as an online course because they're jamming essentially a couple weeks worth of work into a 1 week space. When you consider they're looking at about 5 hours per cohort per session, which is almost double what you would have done in a regular schedule with 5 hours of coursework per week plus an hour and 15 minutes devoted to MSIP, where you would theoretically be working on homework and that sort of thing, plus actual homework at home. So I'm actually a little bit behind, apparently, but I have a feeling that I'm not alone in that. So let's just go through some of what we covered today. First of all, if you had trouble finding the chapter, I apologize for that if it didn't come up, if the link was a bit stale or something. Sometimes you have to sign into your Google account or what have you. If you did not sign into this class using your board email, you should probably do that and then get rid of your other account. Primarily board email is what we want, and there are certain things that don't unlock without a dsbn.org in the email address. I'm not sure when they come up, mind you. So let's have a look there. Okay, so if you go down, what I've posted here was what I figured we should be able to get through today. So it's basically chapter 1, sections 1 and 2. These physics help videos, which I'm just going to click on here. They're great. They kind of break down the course concept by concept. So the first bunch is graphing, and you'll notice that most of these videos are not very long. Okay, so for instance, one of the longer videos is this one that I've brought up that talks about velocity time graphs, finding area. And it's essential that you watch these. This is the kind of stuff I would normally teach in class, but because of the AB cohort thing, A would end up getting the lesson and B not getting it, or vice versa. So sorry, everything's going to be essentially up to you to watch the videos, read through the sections, and do that kind of stuff. So I'm going to shut him down because we're talking over each other. But you can see that the videos are only about 3 to 8 minutes long. So they're not long to go through. You can pause them. I would take some notes as you're doing them. It's going to be a big workload on you. It's not like March where we were just trying to get by. This is actually us trying to cover the courses here. So I'll go back to the classroom. Here's chapter 1, and I'll try to do this for everything we do, is give a separate link to the chapter. Okay. So I'm basically going to use this book as sort of my platform for content. All right. And I don't really have much choice in that. I mean, I've got loads of handouts and things like that, but I want to narrow it down because there's information overload right now. So what you need to do on the readings is go over, make study notes on the section summary, like make a glossary as you go through of new terms. Okay, so you should know what all these words in bold mean. Mechanics being field of physics, you study motion. Kinematics is the study of the motion without looking at why it's caused. The basics of scalars and vectors. You know, a scalar is a measurement that has a direction, whereas, a vector is a measurement that has direction, whereas a scalar is a measurement that has no direction. So, 20 meters east is a vector measurement, whereas just 20 meters of distance is a scalar measurement. 20 kilograms of mass is a scalar, whereas a force of 980 newtons downwards is a vector, etc. So you'll have to be aware of all of the major new terms that come up. And I suggest strongly that you use the Cornell note-taking, which I'll just bring up here. Okay, if you look at Cornell note method. The very basics of it. Try to find it. Here we are. So the very basics of it, you want your name, subject, date, what pages you're working on. You can put, by recall column, you want to put major ideas up there. I would also put new terms and maybe a brief summary of their definitions, not copy them out of the book, but paraphrase them. And then major concepts, you could write in the notes column, examples, that type of thing. And then at the end, sort of a summary of what the major ideas were. Okay, so there's a lot of different ways of doing the Cornell notes, but they're all essentially the same thing, where you break the page up into columns where you've got your keywords, key terms, questions, etc. On this side, you take your summary notes, you can put them in there, and then a general summary at the end. So it's just a good way to divide up your notes. Let me get rid of this. Okay. So again, standing order for the rest of the semester is on readings. You have to make note of new terminology and know what those words mean, be able to use those words in context with what we're doing. We talked about sign conventions today, which is basically assigning a plus or a minus sign to opposite directions. So in this case, for instance, I'll use this guy. If you have, if this is east, then we might say all the numbers positive are going east, all the numbers negative go west. So there's my highlight pencil. So everything on this side of the zero line on say this east-west number line will be negative numbers. Everything over here we would call positive numbers. So for instance, when they do the example to calculate the distance traveled in the scenario on the previous page, we have, where are we here? We have 5 meters plus 10 meters is 15 meters. So we went 5 and then 10 back. The distance is 15, but the displacement is we add these two vectors up. So there's a 5 meter west vector, and this vector is 10 meters east. And when you add them, this vector is actually, this is actually, we went 15 meters east. So the net displacement here would be 10 meters to the east. The total distance is 5 plus 15, which is 20. Okay. I just want to make sure that they didn't make a mistake on how they did this here, because if we're talking about the total displacement from the starting point, if this is the starting point, then the net displacement would be 10 meters, not 15. What did they do here? They did displacement is final minus initial. Okay, I think they made a mistake. Okay, this I don't like here. I think there's a typo here. I wish I'd caught it earlier in class, but now you can see it. The final position is in fact 10 meters, right? But in my mind, the way they've drawn this, the initial position was here. So it should be 10 minus 0, not 10 minus 5. It doesn't look like we started here, depending on the wording of the question. So here's another case where you go from point A to point B, then to point P, point C, point Q, etc. And the distance is the distance between from A to B, and then add from B to P in this first part. But the displacement is from starting to ending. Okay, so it's that straight line from start to end. Displacement has a vector. Distance just has no vector. It is just an amount. Okay. Similarly, if I go from A to B to P to C to Q, my distance is adding up the lengths of all these sides or side segments, but my displacement is from A down to Q along that straight, somewhat diagonal line there. The only time your displacement and your distance are the same is if you don't change direction. So if you go from A to B, that's distance is the same as the displacement from A to B. It would just be essentially that blue line. Now, just as going over the way the book's laid out, which is going to be essentially our, this will be our template for taking notes. Okay, you can imagine that this is something that I would have normally written on the board, but not quite so big. We're going to be, again, using the examples out of the book primarily, and then the practice problems to reinforce these concepts. And I will go over the examples in the book because it's kind of how I have to do it when I'm doing this online kind of stuff. So if you take a look at it, the way the example's set up here, generally speaking, we like to start with a diagram. It doesn't have to be pictorial. It can be like stick figures, etc. But it's always a good idea to start with a diagram to kind of visualize what's going on. Okay, and you're doing two things here. You're going to be, someone starts here and goes there, and then goes back there. Initially standing someone's initially standing to the right, and then moves so that they're 3.5 meters left. Okay, so if we start there and go there, right, you can see that we're moving that many meters to the left. So the positions are measured from the origin. The displacement will be your final position minus your initial position. There's a couple ways we can do it. So here we have displacement is final minus initial. And so we say it's 3.5 meters left minus 1.5 meters right. Well, negative or minus 1.5 meters right is the same as minus negative 1.5 meters left, right? Because right is opposite to left. And so we would give them a different sign convention. I might take a pen here and go, okay, well, that direction can be positive, and then this direction here can be my negative direction. Oh, let me get an arrow there. And this would be my sign convention right there. To convert those directions here into signs or just numbers with signs, I could say that D initial is 1.5 meters left, which would be positive, right, which is positive 1.5 meters. And final position, there should be a little vector hat on them. Hopefully there is. I just don't see it on my screen. Is 3.5 meters left. That's negative 3.5 meters. And so when we do the vector calculation here, final minus initial position is going to be negative 3.5 minus positive 1.5. So you're subtracting 1.5 from negative 3.5. So you're going negative 5 meters. It's like if you're, if it's minus 3.5 degrees and then it goes down 1.5 more degrees, then you're minus 5 degrees. So we're negative 5 meters. So this is 5 meters to the left of this initial spot there. And then you would convert that negative back to left. Okay. So let me get rid of that. I'm going to scroll down a bit. When we're talking about position time graphs, and this is about how far we got today, we got into section 1.2. The slope of the graph, okay, I'll get that back. Come here, you. The slope of the graph is the velocity of the car in a position versus time situation. So the steeper the slope, the faster the car is going. If it slopes up, that means the car is moving in the positive direction from the origin. If it slopes down, that means the car is moving in the negative direction from the origin. And you can see that the negative slope here corresponds to the negative direction there. The positive slope here corresponds to the positive direction there. It doesn't matter if the car starts at a negative position, meaning a position to the, say in this case, the position to the left of the origin. If I'm traveling to the right at a constant speed, then my slope will be up and to the right at a constant speed. If I happen to be traveling to the left at a constant speed, then my slope will be down and to the right, according to this particular sign convention, where we're stating that things to the right of 0 are positive and to the left are negative. Again, here's another example. Oh, by the way, you'll sometimes come across these concept checks. These you don't have to write out, but you should go over them to make sure you are understanding what's going on. Here we see another example. If you read through, student B heads west to the bus stop. Student A walks east to her house. After 3 minutes, student A is 300 meters to the east and student B is 450 meters west. Now you can tell that both students walked the same amount of time, but since student B went farther, their slope should be steeper. And since student B was going to the west, their slope should be in the opposite direction of student A. And so this graph down here tells us that. It tells us that they both walked for 3 minutes. There's the time, so you can see they got their homes at the same time. But that student A went this way, basically went from 0 to 300, right? And student B went from 0 to minus 450. So this line is slightly steeper than that line. It's just unfortunate that the scale of this graph doesn't make this steepness of that slope a little more evident. So if you take a look at the practice problem again, here's 4 different times for these different animals to go a set distance of 200 meters. So they all go 200 meters in the same amount of time in different times. So the slowest animal here, the bear, took the longest time, and you notice that slope is the least steep. The fastest animal, the elk, right, that would be here, the very steepest slope, it got to the 200 meters in the earliest time. So essentially what we're saying is the steepness of these lines corresponds to the speed or velocity, I should say, of these different animals because they were all going forward. This one's a little trickier. Here we have 2 roller skaters or inline skaters. Sorry, I'm old. We had roller skates. 2 inline skaters that start at the same position, right? They're both at 0 position. Anything on this line is 0 position. But skater B waited 5 seconds before they started. So skater A is a 5-second head start. So here you can see skater A starts at the 0 mark and skates for 20 seconds. And here skater B waits for 5 seconds before they start. And then they skated for additional 15 seconds. Now, they met up right around there. Okay, that would be roughly, if you take the graph straight down, that's roughly at, let's say roughly at 15 seconds. And if you go across from, if you interpolate, so what I'm doing is I look at where they met up, and I kind of missed it, but if I do a dotted line up like that, they go there, and then that's roughly bringing it across from here. This should be a nice straight line, but I'm using a mouse so you can see that this time go across over to here, a little under 80, so we can estimate it at 75 meters. This is called interpolation when we just read a graph. Remember, sometimes we like to give fancy names for stuff in science so that we can have a bigger paycheck. All righty, so scroll on here. We're not going to use the motion sensor. So when you do the check and reflect, I think I assigned questions 2, 3, 4, 5, 6, and 7. These go pretty fast. I did get questions on this one primarily of describing the motion. It depends how specific you want to get. I would just say that the motion below the object or what have you, it has started at a position of 0 and moved at constant speed for 4 seconds to a position of plus 16. Then it stayed still for the next 8 seconds and then went back to the origin in the next 4 seconds. But you need to understand that this is all one-dimensional motion. So this thing essentially went west, stayed there for 4 seconds, and then went back east. So the net displacement is going to be 0 because I started at 0 and I ended at 0. So my displacement is 0. My average velocity for that trip would be 0 because my displacement is 0. So I went from here back in there. I didn't go up a hill and stay on the top of the hill and then go down the other side. Okay, this is a numerical representation of the velocity along a one-dimensional skinny little pathway. So that's how to interpret those. If you have any trouble with these, then message me through Google Classroom and I'll go over them. Now, when you get to speed and velocity, remember, speed is a scalar, velocity is a vector. So if it's got direction, it is a vector. If it doesn't have direction, it is a scalar. So your odometer, I was showing a needle, but your odometer shows distance. Your speedometer shows speed. Your speedometer in conjunction with your GPS could show you velocity. So if you're driving down the QEW, Niagara Falls to Fort Erie at 100 kilometers an hour, you're going approximately 100 kilometers per hour south. But your speed is 100 kilometers per hour. Okay, so you have to keep that in mind. Non-uniform motion means the velocity changes from time to time, and that could mean the direction changes. Uniform motion means one speed, one direction for the whole trip. Average speed, really you take your total distance. So if you ran around a 400-meter track twice and it took you 2 minutes, then you would have gone a total distance of 800 meters in a total time of 120 seconds, and you could figure out your velocity from there. You'd be 800 meters divided by 120 seconds, and you would get your speed in meters per second. Okay. Now I want to show you what I've posted again in our classroom. So let me just grab it here. This is going to be a long video. Sorry, guys. I'll end with this and then I'll do another one. Hopefully it'll upload. So, but I've also put in here in the classwork section under textbooks and formula sheets, I put this kinematic summary. This is a reference sheet for you guys. And it basically allows you to figure out these physical quantities from these 3 types of graphs. And again, watch the videos first. So if I want to find velocity from a DT graph, I find the slope of a line segment. Okay, I say line segment because we talk about uniform velocity is only uniform as long as the line segment on the DT graph is straight. Instantaneous velocity, we find the slope of a tangent line. So what that means is if I have a DT graph that looks like this, and I want to know the instantaneous velocity there, I have to find the slope of that line segment. So I would take my ruler right at that point and make sure that the angle immediately before and after the point is as close as I can get it, and I would take the slope of that line. It's tedious and it's a bit inaccurate, and I would explain it more, but you have to know calculus to really understand the concept of that. So this is from a DT graph. Okay. So basically, if you go over this, anything you want to find, any of these physical quantities you want to find, it tells you how to find them from various graphs. And you notice that the VT graph has the most information on it. So we're going to spend the most time with that. Eventually, as we're going to see, the VT graph will lead to these 5 equations of motion. You don't have to worry about those yet. We will be looking at those probably in the next section. I don't think we'll get to it on my next lesson. By the way, here's what I'm going to be doing. I'm going to be posting the work for your class early in the morning of whatever day it is. So I posted what is, I'm hoping, approximately 5 hours of solid physics work. And if it's 6, well, okay, you're taking physics. That goes in the territory today. And on Thursday, I'll be posting the part 2 for the week. Okay, so I'm not going to dump it all at the start of the week. This is a little bit different than in March through June, where we were only giving out roughly 3 hours of work for the whole week. Here we're giving almost quadruple that. So be prepared. Okay, if you get buried, let me know. Let's help each other through this. So I'm going to go back here. All righty, where was I with my chapter? I go with it. Oh, here we are. It's in the stream. And where have I gone here? Too far? No. All right. So speed and velocity. I'll scroll through. Okay. That's better. Okay, so in this practice problem, a person runs 10 meters east in 2 seconds, then 5 meters east in 1.5 seconds, and 30 meters west in 5. Find the person's average velocity. You can't just find, okay, you can't do 10 over 2 plus 5 over 1.5 plus 30 over 5 and divide those by 3. You've got to find the total displacement over the total time. So V average, okay, V average is total displacement, and I'll put a little TOT for totes displacement, over the total time. And it takes me a while to draw with this thing. So that means I'm going to do 10 plus 5 minus 30, because I'm going to use this sign convention where that's positive and that's negative. Now, so I'm going to apply my sign convention. So it's going to be 10 plus 5, which is 15, minus 30, which is negative 15. And just to get around me trying to click on all that stuff, I'm going to say, okay, I got negative 15 meters. All right, so that means west. And I've got a total time of 2 plus 5 plus 1.5 plus 7. So I've got 8.5. Why can't it be 7.5? That would make for nicer math, wouldn't it? So 8.5 seconds, right? And you'll get, when you round it off to 2 significant figures. Now remember, you were supposed to have done the math and data stuff, the measurement and calculations. So I only have 2 significant figures here and 2 significant figures here. So I have to round it off to 2 significant figures. That's where this 1.8 meters per second west comes from. The negative means west. The units are meters over seconds, and the magnitude there is 15 over 8.5, rounded off to 2 significant figures. All right, this video is going to be really long, and I'm going to post it up, and when it's, or I'm going to let it compile, and when it does that, then I will post another one. All right, signing off for now. Good luck, everybody.